Welcome back. Now here are some more results. Theorem 4, let m be a positive integer. The integers a and b are congruent modulo m if and only if there is an integer k such that a is b plus km. Let's prove this carefully. It's again an if and only if. So you need to prove the one-way direction and the converse. Okay. So here is proof of theorem 4. How do we prove something like this? If and only if, right? So here is a proposition. The integers a and b are congruent modulo m. Assume that, suppose that a and b are congruent modulo m. Okay? Assume that, and now we want to prove the proposition there is an integer k such that a equals b plus km. All right. So that's one-way direction, if you like. That's one-way direction. Okay, we will prove the reverse later. So let's worry about this direction. Suppose that a and b are congruent modulo m, as a and b are congruent modulo m. What does this mean? We have a minus b is divisible by m. What does that mean? That is, there is an integer k such that a minus b is m times k. Therefore, a equals b plus m times k, which is what they wanted us to prove. We wanted to prove. Okay, so we have proved this direction of the theorem. Right? Now we want to prove the reverse arrow. Let me look for reverse double implication. I don't seem to find. There you go, left arrow. Okay, so that's onward. So now we are going to suppose that a equals b plus for some integer k. Well, what does that mean? That is, a minus b equals mk. What does that mean? That is, m divides a minus b. Hence, a and b are congruent modulo m. All right. So these are straightforward. Following the definitions, you can carefully prove these results. So similarly, prove the following. Take some time. Just follow the definitions. These follow. Okay. Let m be a positive integer. If a is congruent to b modulo m, that is, a minus b is divisible by m, and c is congruent to b, this should be d, mind you, sorry, this should be a d, then a plus c is congruent to b plus d, and ac is congruent to bd modulo m. You can show this carefully, mind you, this should be a d. Likewise, simply following the definitions, you can show let m be a positive integers, a and b be integers, then a plus b modulo m. So the remainder when a plus b is divided by m is actually equal. You take the remainder when a is divided by m, take the remainder when b is divided by m, add those two remainders and find the remainder when the sum of remainders is divided by m. That is a plus b mod m. Likewise, a times b mod m. You take a mod m, take b mod m. So these are remainders. Multiply them, divide that by m and find its remainder. So show this using simple definition follow, and you will see things fall in place. Which brings us to arithmetic modulo m. So with all this information, so I'm leaving theorem 5 and this small lemma for you to work out. It's not that bad. We are now ready to perform arithmetic modulo m. So Zm is a set of non-negative integers less than m. So once you fix a positive integer m, take all the integers 0 until m minus 1. That set is denoted by Z sub m. There is a possibility of doing something with these numbers. Okay, this set represents all possible remainders when an integer is divided by m. You can define a plus sub m and a dot times m. So a multiplication and an addition in Zm, which is defined like so. A plus mb is a plus b modulo m. A times mb is ab modulo m. Okay, these are arithmetic operations satisfy closure, associativity, commutativity, identity, additive inverses, and distributivity. You can build addition, multiplication, inverse table, multiplicative inverse tables for Z10 and Z11. Okay, this is something that you need to go over a bit carefully. Let's go through Z10. Okay, you will see what we mean by multiplication, closure, addition and multiplication modulo m. So you want to study Z10. So what are the elements here? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So for 10, you start from 0, go until 9. All right. Whereas for Z11, you would start from 0, go until 10. That's the point. You start from 0, go until 1 less. All right. So now let's understand what it means to add numbers in this modulo m. Okay. So let's see. Suppose I want to add in modulo 10, right? See, if I want to add 5 and 7, 5 plus in modulo 10, 7 is what? Well, you take 5 and 7, 5 plus 7 is 12, and then divide by your m and look for the remainder. 5 plus 7 is 12. When I divide 12 by 10, remainder is 2. That's how, you see, 12 is not here. I need something from here. You add these two, divide by 10, look for the remainder. Say I multiply 5 times in modulo 10. So 5 times 7 is 35. Modulo 10 is 5. So I divide 35 by 10. What is the remainder? So basically answer is a remainder. That's why it will fall here. Now let's look at the same two numbers in modulo 11. 5 plus 7 is 12. 12 divided by 11 was the remainder 1. So 5 times 7 is 35. But modulo 11, what is 35? Divide 35 by 11 was the remainder 2. You see the distinction? So this is what the addition and multiplication is. All right. So with this, you have most you can see that you can add and multiply. 0, adding 0 gets you back the same number, so 0 is additive in identity, 1 is multiplicative identity. Who gets me 0? Suppose I want to find 5 plus 5 plus something to get me 0. What should that be? There is no negative 5 here. But notice what is 5 plus 5 in modulo 10. 5 plus 5 is 10. 10 divided by 10, remainder is 0. What about something plus 7? Well, 3 plus 7 modulo 10 is 0. All right. Something similar, 5 plus what equals 0? Well, 5 plus 6 in modulo 11 is 0. All right. So that's how you find additive inverses. You can build addition and multiplication tables and proceed from there. Okay, the rest is just straightforward. There is a difference between a field and a ring. So ring is where you can add, multiply, find additive inverses, but you are not guaranteed multiplicative inverses for non-zero elements. In a field, you are guaranteed multiplicative inverses. Okay, so this completes this particular lesson.